a basic calculation, and that gives you 0.375 kilopascal. You don't have to apply any Bernoulli's equation, any continuity equation. Straight away you can reckon, because now let's try and apply fluid mechanics and dig out some important technological facets about the design of this product. If you looked at the compressor, the pressure is continuously increasing. Therefore, from the language of fluid mechanics, you can say that the compressor is subjected to adverse pressure gradient. Across turbine, the pressure is falling. That means it is subjected to favorable pressure gradient. What is the consequence of this? This actually means now in this discussion we would discuss two situations on fluid mechanics, one from GATE 2020 and another from typical research interview. Now both these questions are based on the concept of force exerted by accelerating fluids. Now here the GATE 2020 is a simple question. The fluid is made to pass through a converging nozzle, thereby you are accelerating it, and then it impinges a static wall, and we need to find out what is the pressure at which it impinges the wall. Now it can be done using standard fluid mechanics equations, but for GATE we need to adopt a lateral approach, which is not conventional. It can save a lot of time. Of course, in the course we have detailed it by the conventional way also. Now let's see what exactly is happening. The fluid is entering with certain velocity and certain static pressure, and the gauge pressure is said to be 0.36 kilopascal. That means the total pressure head at this particular point is 1.36. So now it is expanded fully to atmospheric pressure. That means it started with a dynamic head and a static head, but now everything is converted into dynamic head because it is expanded to atmospheric pressure. Now it started with certain velocity V0. Since this nozzle is accelerating because the area is decreasing, if you use a continuity equation, you can clearly see that as area decreases, the velocity increases. And you can see from the numericals given, the area in fact decreases 5 times, and in order to ensure continuity, the velocity must increase 5 times. VA is constant, right? But what is to be also noted, that velocity is proportional to a root of pressure, or velocity square is proportional to the pressure. That means if the increase in velocity is 5 times, then if V0 is the initial velocity, then the final pressure becomes 25 V0 square. Now since it is completely the dynamic head here, there is no static pressure head here. So this represents the complete pressure that the static wall is going to see, because the fluid is going to impinge the static wall. Now it started with V0 but ended with 25 V0 square. So that means by conservation of energy, 24 V0 square should be equal to 0.36 kilopascal, which is the pressure to begin with, because it was V0 and 0.36 kilopascal, that is the gauge pressure to begin with. Now since it is expanded to atmospheric pressure, all the static head is converted into dynamic head, and it is 25 times the initial velocity square. So we know the value of 24 V0 square, because initially it was V0 square plus the pressure. So therefore 25, if I split into V0 square and 24 V0 square, then 24 obviously refers to 0.36 kilopascal. What about 25? If 24 is this pressure, what about 25? A basic calculation, and that gives you 0.375 kilopascal. You don't have to apply any Bernoulli's equation, any continuity equation. Straight away you can reckon, because increase in velocity 5 times is a very straightforward reckoning from the figure, because as area decreases 5 times, and then the pressure is proportional to velocity square is also a very fundamental understanding in fluid mechanics. So therefore the pressure that is exerted on the static wall is 0.375 kilopascal. Now let's move on to a research situation in fluid mechanics. Now let's consider the research situation for fluid mechanics. Look at this typical spool of a gas turbine engine. Typically, depending on the makers, either a gas turbine could be of 2-spool or 3-spool type. When I say spool, it is a mechanically independent assembly running at a different RPM compared to other spools. Now let's try and apply fluid mechanics and dig out some important technological facets about the design of this product. Now the first reckoning is obvious. If you looked at the compressor, the pressure is continuously increasing. Therefore, from the language of fluid mechanics, you can say that the compressor is subjected to adverse pressure gradient. Across turbine, the pressure is falling. That means it is subjected to favorable pressure gradient. What is the consequence of this? This actually means that per stage of turbine, you can generate significant amount of power, and per stage of compressor, the power that could be absorbed, because compressor is a power absorber and turbine is a power generator, is very limited because of adverse pressure gradient. That means if you looked at a typical compressor blade, it is cambered very less compared to a typical turbine blade where the camber is significant. That is, flow turning angles are significant for turbine blade. It is very limited for compressor blade, because there is a possibility of flow reversal, and that in turn leading to stall and surge, two important phenomena for any compressor. Now, if you observe the design carefully, single stage of turbine therefore is able to drive several stages of compressor, because one stage of turbine can develop a huge amount of power. In fact, you would be mind boggled to learn the fact that at takeoff, when the engines are developing maximum power, a typical civil engine blade, turbine blade, can develop up to 800 to 900 horsepower. So therefore, a loss of a turbine blade can be extremely significant for an engine. Now let's come to the second technological facet that could be unearthed from the fundamentals of fluid mechanics. If you looked at the pressure forces that are acting, if you calculate pressure into area for a typical compressor, you can see that the net aerodynamic force is acting in the forward direction, and similarly the net aerodynamic force for the turbine is acting in the rearward direction. When I say forward and rearward, these directions are referred to the direction of motion of the aircraft. That is, the compressor is experiencing a force, a net aerodynamic force in the direction of travel of the aircraft, and turbine exactly in the opposite direction. These forces are obviously different, and therefore the differential force of turbine minus that of the compressor must be supported by a thrust bearing. That is why each spool, if you observe a typical cross section of a gas turbine, each spool has one devoted ball bearing that actually supports the thrust load. And that is why you cannot have a roller bearing which predominantly supports radial load, but whereas a ball bearing which supports predominantly the thrust load and to certain extent radial load is the best choice to support the differential load of compressor and turbine. This is one of the major organic takeaways. By applying the principles of physics systematically to a product, you can dig out several unobvious facets of engineering design. Now, one of the important statements we would like to make in fluid mechanics, it is always easy to accelerate a flow that is, I'm talking about turbine situation, than to decelerate a flow. Because if you try to decelerate, it is like a cyclist who is trying to climb a mountain actually comes off. And the same way, if you try to create too much of adverse pressure gradient, the flow may get separated. So therefore, it is very, very important that we apply fluid mechanics very rightfully and thoughtfully, so that you can unearth the design facets. Not only that, we also appreciated the fact that by basic fundamental reasoning, that is, pressure is proportional to velocity square, we could crack the gate fluid mechanics problem just like an arithmetic problem without resorting to any classical fluid mechanics equations. So therefore, it is always important that how well and how effectively you apply the fundamentals of physics that you learn. So let's continue.